Today I want to talk about a problem of parameter estimation, which is finding the essentially how deep the ocean is, or rather the shape of the bottom of the ocean. I'll spend a lot of the talk probably describing the problem because it'll take a little while to get all the details down. But what I really wanted to highlight is how observers sort of come in to this problem in a somewhat natural way and allow us to accomplish something. So it's a nice application of the observers to a parameter estimation problem. Okay, so this is joint work with my student Manisha and my colleague Didier from Nice. I'd like to acknowledge some support from several institutions, and the work is mostly based off a paper in 2021 that came out about this topic. Okay, so let me first describe the problem. So the physical setup is there is a layer of fluid, water, that is on top of a solid boundary. Okay, so here I've drawn the free surface of the water, and here there is the solid boundary, right? So the boundary is located in the z coordinate at this position. So this profile zeta describes how the bottom boundary is shaped, and the profile eta describes how the free surface is as a function of space and time. Right? It's a free surface, so it should evolve in time. And then there's something like a mean depth h, and sometimes we talk about this water column, which is just the sum of these three quantities. So you can imagine, I don't have a video, just use your imagination, that this is moving in time, and you're able to see the shape. So let's just say somebody gives you this graph, eta, as a function of x and t, okay? You might ask, well, how on earth would you ever do that for the ocean? Typically, it's a satellite measurement. Something like synthetic aperture radar will give you some estimate of how the shape of the surface of the ocean looks like. It is only a shape, which is not to say you don't know where the surface is located, because if you knew where the surface is located, you actually know where the bottom is. Right? So you only know the shape, right? Okay, and the goal is, given the shape, find the shape of the bottom. Okay, sort of a classic inverse problem. It has some relationship to a problem that you may have heard of. Can you hear the shape of a drum? Where you basically see the vibrations or hear the sounds, which is the eigenvalues, and you want to figure out the shape of the drum. Think about the drum being given as the bottom boundary, and the waves are somehow oscillations that you can see. And that's what you want to back out. So it's a much more complicated problem than hearing the shape of the drum, but there is a relationship that we'll see pop out naturally. Although I won't be using the exact analogy. Okay, so how does the surface boundary move? As I said, the graph is given by eta. It's going to change in time, so it has a time rate of change, right? The time derivative of eta. And it's not hard to convince yourself that the only way that the shape can change is if the local normal velocity is different from 0. Right? That's the way the shape will change. If the tangential velocity is the one that's non-zero, that won't change the shape. That'll just change a parametrization of the shape. But if you actually want to change the shape, you need a normal velocity. So the key insight from a sort of physical point of view is that the velocity normal to the free surface is actually this time rate of change of eta. So when we are seeing the shape change, if we can measure eta as a function of space and time, we have access to the normal velocity component at the surface, because we can take a time derivative, and that's an estimate of what that normal velocity is, right? If we're working with data, it's an actual estimate. If we have the exact form, it's precisely the normal derivative. Okay, the bottom boundary also has a normal derivative, the fluid velocity at the bottom boundary, you can also define the velocity normal to it. And because this shape doesn't change in time, the normal to the bottom boundary is 0. The velocity normal to the bottom boundary should always be 0, right? So this is sort of establishing a relationship between the time derivative of eta and velocities of the fluid normal to a surface. This is something you want to absolutely remember for this talk. I'm going to be repeatedly using this idea. Velocity is normal to a surface will give me the time rate of change of this free surface, and the velocity normal to the bottom boundary should be 0. Okay. Okay. So at this stage, if we think about the problem that we have, which is we were given eta as a function of x and t, and we want to find zeta as a function of x. What we know is this normal velocity component, and we know that somewhere the normal velocity should vanish. Right? We know that the normal velocity is non-zero here. Somewhere here, the normal velocity should vanish. So what we really need is a way to relate normal velocity at one point to normal velocity at another point. Keep in mind that the velocity that is normal to eta should depend on the surface velocities, that is the velocity fields at the surface, which is something we do not have. Right? So I'm trying to establish what information we know and what information we don't know. We know the total time, we know this time derivative of eta, we don't know these surface velocities. Right? Okay, so one of the things that we will need to fill in is a way to capture those surface velocities. If we want to do this problem, we need to also answer, how do you find the surface velocities along the way? You can't just do it alone, okay? All right. I'm going to give you two hand-wavy arguments as to why this problem is hard, and then I'll put a mathematical formulation and get those two difficulties back again in a mathematical framework. First thing that the problem is hard, if you just have a flat surface, you won't be able to tell just by looking at the surface whether the water is in this teapot or in this jar. Right? Flat water can fit into any container, which means you should not be able to tell the bottom boundary if the water is flat. This is a form of ill-posedness, which is basically saying there is data, eta equals 0, that corresponds to an infinity of solutions of the bottom boundary. So if you want to sort of invert this map, you've got this null space going on, right? You can't find the bottom boundary when the fluid is static, which is to say we need to use generic time-dependent, spatially dependent data. Don't use some special symmetric data set that sort of has some special property. You won't be seeing everything that's happening at the bottom. What it also says is that the velocities at the surface should be non-trivial. Right? So they should be non-zero. There should be movement at the free surface. If I wanted to know the shape of the teapot, I need to shake the teapot and create waves at the surface. Those waves are a result of the shape of the teapot. Right? Otherwise, I won't have that information. Here's another hand-wavy reason why this problem is hard. If I imagine that the ocean is infinitely deep, what tends to happen to the velocities is as you go deeper and deeper, the velocities decay and go to 0. Okay? What does that mean? Well, first of all, let's define what I mean by deep. Think of a ratio of two numbers, a depth of the fluid and an object of size L. This is like an aspect ratio. If you're talking about me swimming in the deep ocean, that aspect ratio is about 2,000. Right? I'm not very big compared to the depth of the ocean. If, however, you take a typical tsunami wave in the deep ocean, the horizontal extent of the tsunami wave is so large that it is thousands of times larger than the depth of the ocean. Right? So a tsunami wave is always in shallow water. even though I could be swimming in the ocean at the same time as a tsunami wave was going by. The tsunami is in shallow water, I'm in deep water. Okay? What that really just says is that the horizontal extent of the object dictates whether the object is to be considered in shallow or deep water. Okay. Another way to sort of think about what is the horizontal extent, 1 over L is really like a wave number. So if we think about non-dimensional wave numbers, when these non-dimensional wave numbers are large, then we're in deep water. When they're small, we're in shallow water. Why am I talking about wave numbers? Because I ultimately want to bring in some Fourier theory. And in terms of Fourier modes, the small wave numbers are the ones that I think I can actually infer from the bottom. If the bottom feature is a localized disturbance, then a localized perturbation or disturbance requires high wave numbers to localize. High wave numbers belong in deep water, and so it is hard to see them, right? This is this sort of hand-wavy sort of idea that any kind of localization, if the object I'm trying to detect is a localized bump, then I need a lot of wave numbers, and that's going to be hard for me to detect. Long features, large features are going to be easier to detect. They're the ones that are in shallow water. Okay. So let's put this in more mathematical terms. We'll have to make some assumptions. We'll assume that the fluid is inviscid, irrotational, incompressible. All of that put together says the fluid velocity is given by a gradient of a potential. Right? We call that potential flow. And because of the incompressibility, this potential is actually a harmonic function in the fluid domain. Okay? So this is really nice because we were talking about relating things on one boundary to another boundary, and sitting in between is a elliptic PDE. So we sort of think, okay, maybe we can relate values on a boundary to values on a boundary. These maps are well defined. Okay? So rephrasing what we have. Given the Neumann condition on the free surface, given eta t at eta, find where the Neumann condition vanishes. Like that's the rephrasing of the problem. There is a harmonic function on one part of the domain, you know the Neumann condition, and you want to find where the Neumann condition vanishes to conclude where the other part of the domain is. Yeah. Why should the Neumann condition vanish at this part? Because that's the normal velocity. So the boundary is the location where the normal velocity vanishes. Okay. So the way people attacked this problem was they actually made it easier. They assumed more. What they assumed was, we're not just given the Neumann condition at the free surface, assume you're also given the Dirichlet condition at the free surface. So at one surface, you're given the Neumann and Dirichlet condition, and then there's a harmonic function, and you want to find where the harmonic function has a zero Neumann condition somewhere else. Okay? So if you think about it, what people are actually proposing you do, and this is the standard way to do this problem, and this is part of the reason why it's ill-posed, is you're supposed to solve the Laplace equation as though it were an evolution equation by giving two boundary conditions on the same boundary, and then evolving the solution in Z downwards and computing where the normal velocity vanishes. This is why it's ill-posed. This is the classic ill-posed problem that we all sort of learn in our first PDE course. You're not supposed to solve the Laplace equation as an evolution problem. But that is precisely the question that we have to do here, right? In part, this tells you why shallow water works better. If the fluid is shallow, this distance is in some sense small. So even though it's an ill-posed problem, the growth rate of any kind of solution due to a perturbation or a noise might not have grown that much. Right? So in some sense, you get an idea of why shallow water, from a mathematical perspective, should be a better idea. Okay, so to summarize the difficulties with this problem. You've got to avoid trivial surface velocities. Always use generic data. You've got to stay in the shallow water regime, whatever that means. You also need to know the Dirichlet condition, right? Which is not something that the original problem suggested we had. We only had knowledge of the surface. And of course, there's going to be this issue that solving these kind of elliptic boundary value problems where we supply all the information on one surface, that's got to be ill-posed. There's going to be a sensitivity noise issue. That's all a problem, right? And the point of the talk is to say that this step, observers will come and help us. Okay, there are multiple steps. Observers are not going to help us in everything. We're going to have to make some other assumptions to sort of resolve the other issues. And I'll sort of give you a spoiler. The last bullet point is going to remain a problem. Right? We are not going to get rid of that in a satisfactory manner. That's an open problem. Okay. All right. Okay, so I need to introduce a new object that some of you may or may not know about. It is called the Dirichlet-Neumann operator. So the Dirichlet-Neumann operator is a linear operator. So it's an operator that eats a function, and the function it eats is the Dirichlet condition at the free surface. And it assumes a Neumann condition at zeta and solves this Laplace equation. Given that solution, you now compute the Neumann condition at the free surface. So it's a map from the Dirichlet condition at a boundary point to the Neumann condition at that boundary by solving the PDE, right? Assuming there is a boundary somewhere else, right? So that's why G is actually a function of eta and zeta. G is a function of eta and zeta that takes a Q and maps it to the Neumann condition. So we map the Dirichlet condition here to the Neumann condition. Okay. For nice geometries like rectangles and circles, you can actually find out what this G operator looks like. For arbitrary domains like this, it's not easy to compute. Right. Nonetheless, we know a lot about it. If we assume suitable regularity for these graphs, eta and zeta, you know that this Dirichlet-Neumann operator for fixed eta and zeta is a map between these Bepo-Levi spaces, h dot 3 by 2. This is just telling us that they are sort of well-defined objects. We understand how the regularity changes. We understand a lot about these problems. A good reference is this book by David Land, on actually the water wave problem itself, but there's a long discussion on the Dirichlet-Neumann operator, its properties, in particular, the fact that it's actually a self-adjoint operator on L2, and then there's this earlier result that actually said the operator depends analytically on the surfaces. So it's what you can think of it as G has a Taylor expansion in terms of operators, right? And those operators are and those operators are like individually homogeneous of order P in eta and zeta. That's the sort of Taylor expansion idea. Okay, so we know a lot about this. This is really useful stuff. And so let's ask about how we can use this operator in the context of this problem, which is if I give myself the surface, the Neumann condition, and the Dirichlet condition, which is definitely too much information. But if I assume all of this, there's this nice result from 2017 that says you can actually find the bottom profile through this minimization problem. Right? And if you think about it, what is this minimizing? It's just saying that G should map the Dirichlet condition to the Neumann condition. You're given the Dirichlet, you're given the Neumann, you choose a zeta, you see if that works. If it doesn't, update your zeta. Do some sort of gradient flow, right? That's essentially what this is saying. They prove a nice result, basically saying that you can uniquely identify the bottom boundary. Uniquely identify the bottom boundary. This minimum exists, and it is the unique solution. Essentially, the argument is elliptic continuation, or if you want to think about it in 2D, analytic continuation. That's why the uniqueness comes. Right? There's only one harmonic function which satisfies that Dirichlet condition, that Neumann condition on that boundary. Okay. The only problem is, and they mentioned this in the paper as well, is that the minima that you get is highly sensitive to noise. So if you perturb eta or the Neumann condition or the Dirichlet condition, you can change zeta quite dramatically. This is well known in stability, and this is essentially the same problem that we've always seen of Laplace equation, the Hadamard instability that you have. That's exactly the problem, this sensitivity to noise. Yeah. The other issue, of course, is nobody knows how to measure Q. Right? We only know how to see the surface. We do not know how to measure the velocity potential on the surface. So nice result, but it doesn't really answer the question. Because in some sense, we need to figure out Q. Okay. So, as I said, we should expect deep water to be ill-posed. Let's see it from a mathematical perspective. As I said, the Dirichlet-Neumann operator has a Taylor series. And so you can expand this operator in this form. You can actually compute these things, if you want, by hand. There's a recursion formulae. It's easier to compute numerically, although also challenging at some point, because you just have to compute higher and higher derivatives. So you should really think of these as pseudo-differential operators. They're essentially multipliers in k-space and multipliers in x-space. It's just a sequence of multiplications. Right? So here, to say that you take d tanh hd, essentially take a Fourier transform of q, multiply by k hyperbolic tangent of k. That's what that expression means. If you go down this series, what you see is when zeta first appears, linear in zeta, you've got this operator which corresponds to multiplying in Fourier space by a hyperbolic secant. Okay, so the output, the normal derivative, the Neumann condition, is influenced by the bottom boundary through an operation of multiplying by a hyperbolic secant in k-space. Hyperbolic secant goes to 0 rapidly. So it cuts off all the high wave numbers. Right? And if you want to find zeta given this, like if you think about an implicit function theorem, you want to say that the derivative of g with respect to zeta should be a boundedly invertible map. Well, that's just not true because of this hyperbolic secant that we multiply it by. It's like dividing by hyperbolic secant. That is a very dangerous thing to do unless the thing you're dividing by also has the same rate of decay. And if it doesn't have the same rate of decay because of noise, you're essentially going to get something that doesn't sum up to be in L2. Okay, so this smoothing effect of the forward map has to be inverted. Whenever you smoothen the forward map, inverting is going to be a problem. Right? Think of any other map that smoothens, a convolution. Deconvolution is hard. Right? Diffusion, good in the forward. Removing diffusion is hard. Right? Same thing is happening here. So high wave number features of the bottom boundary are getting smoothened out as an effect. If I want to recover the high wave number features, I have to divide by this operator. That's going to be a bad thing. Okay. So we expect bottom profile reconstruction is easier in shallow water. Okay, so let me go back to the list of difficulties. Avoid trivial surface velocities. So we're just going to have to assume the data is nice and generic. Stay in the shallow water regime. The interpretation of that statement is now approximate the original Dirichlet-Neumann operator by an operator that is suitable in the shallow regime. What do I really mean by that? This Taylor series should be truncated somehow. Right? truncate this Taylor series or replace that hyperbolic secant by something that can be divided by. So, take a Taylor series of a hyperbolic secant. Just keep the first few terms. Okay. That's really what we're going to have to do. So this is a modeling result, really. As I said, we're going to use observers, and the sensitivity to noise issue is going to persist in some sense. That is inherent in the problem. Okay, really not going to get around that point. All right, so how are observers going to come into this? We know that observers have got something to do with time-dependent equations. So far, I've been talking about an elliptic PDE. So I have to now tell you, how do things evolve in time? Okay, so how do they evolve in time? Same equation, there's a harmonic function in this region, and recall the time derivative of the surface, the Neumann condition, was given by this Dirichlet-Neumann map. So you could ask yourself a question, hey, this is an equation for eta. Is there a time equation for q? Time derivative of q equals something. Can you tell me how q should evolve in time? It turns out, yes, essentially due to this original paper by Zakharov in 1968, and then Craig Sulem used this result and gave the Taylor series the first time. Essentially, there's a Hamiltonian. If that word means something to you, well and good. If it doesn't, just think of it as an energy. Okay? And the equations of motion can be written purely in terms of this Hamiltonian. So you have to differentiate this Hamiltonian like a Euler-Lagrange style like functional derivative. You recover the equation for the eta, and you generate an equation for q. If you know anything about Hamiltonian equations, think of q as the conjugate momentum to the position. If that means nothing to you, that's okay. We're never going to use that structure, but that's the relationship between these two things. Right? So in some sense, knowing eta and q was a natural thing to sort of suppose they are a coupled system of equations. This is a coupled nonlinear set of equations. And actually heavily non-local if you think about what G actually is. G, in terms of how, like what is the order of the nonlinearity in eta? It's infinite order, because it's got a Taylor series in eta. Right? This is a very nonlinear, very non-local differential equation. Okay, so what I said was we have to get it to the shallow water regime. The answer is kind of simple. You basically replace this G with a different G. Like that's the modeling aspect. Change the Dirichlet-Neumann operator to another operator, right? So formally it looks like this, and this is what the equations that you'll generate with this choice. The choice of GM is largely a user-dependent choice. What are you interested in modeling? Which features are of interest to you? You can go to the deep limit, you can go to the shallow limit, there's a G for each one. Land's book is a great resource on how to derive these G's and their relationships. Right? So he tells you if you truncate it at this order, this is the error, this is what it looks like. So we've got a nice prescription to replace our difficult problem with possibly an easier or simpler problem. Physically, you can just think of all of these equations as nonlinear wave equations. So think of your usual wave equation, add a bunch of nonlinearities. Technically, they all are dispersive wave equations, so they're not just the hyperbolic wave equation. They can be dispersive as well. But that's just, that's at this stage, that's just a detail. You can just think of making a choice of replacing the original problem with an easier problem. Whereas the original problem has an infinite order nonlinearity, is heavily non-local, these problems can actually be local and have quadratic nonlinearities depending on the choice you make, right? Depending on how simplified you want to make your problem. Okay, so how are observers going to come in? We've got a model for eta and q, and we've measured eta. So let's just add a Leuenberger observer to this equation. So we'll have to choose our lambda and nu, these observer parameters, so that the system is stable and converges to sort of the state that corresponds to eta. Recall, this is still a nonlinear differential equation. Our theoretical understanding is only for the linear part, and we've got a lot of numerical results to suggest that convergence happens even for the nonlinear case, with the same observer parameters. I don't change them. So the idea is, if you just want to do velocimetry, which is find q given eta, you're going to assume that eta and zeta are known, and it's not too hard to show that there is a choice, constructive choice. We give you a recipe for lambda and nu, such that you actually get convergence for the linear case, even when the zeta is there. Right? It's a variable coefficient problem. Even for the variable coefficient problem, it'll converge. The nonlinear problem, we just have numerical results. But the rate of convergence seems to be the same. We can't really explain much of that. So at the end of this slide, what you realize is, if you knew a zeta, you could find a q. Right? And then the other result was, if you knew a q, you could find a zeta. So you kind of want to combine these two, right? And say, I can do both simultaneously. That's the basic idea. Okay, so simultaneous velocity recovery and bathymetry. Suppose somebody gives you data, eta as a function of space and time, and suppose somebody also tells you a model. Right? So it's reconstruction in the context of a model. Model is dependent on a choice. We are saying, for a whole family of models, we can repeat this process. So it's not a particular model. If you want to pick another model and see the consistent reconstruction, we can do that. So somebody gives you data, there is a model, and start with some estimate, which is not the true bottom boundary. You can use the incorrect bottom boundary to get an estimate for Q, the Dirichlet condition you don't know. And then you can use this reconstruction idea of a minimization problem to find a better estimate of the bottom boundary. Right? And the hope is, starting from zeta tilde, at the end of step 2, the zeta that you get is somehow more accurate. And the point is, you actually have to choose these parameters carefully. Okay? So it's a two-step process. First, find the velocity with a guess of the bottom boundary. Then, with the estimated velocity at the surface, update your knowledge of the bottom boundary. Okay, so let me talk a little bit about this second step, where we have to do this minimization problem, where we want to find the zeta that sort of minimizes this. If I chose my model such that my model G was linear in zeta, then this is actually just this boils down to like the normal equations, least squares, right? AX equals B. That's essentially what this is at this point, if I chose my model correctly. So model choice is important. We can prove a whole bunch of stuff about this particular operator when G is linear, that it's a self-adjoint linear operator, happens to be bounded if you make the right choice of the model, and that the spectrum is contained in the negative real axis. So all of that is to say, yes, you can choose any G, but some Gs are better than other Gs. And you have to sort of pick those that are amenable to analysis, right? That are amenable to the reconstruction. We can say some more stuff based on the choices we make. So regularized Boussinesq is a name for a particular model. In that case, this operator B tends to be compact. If you think about what we want to do in order to reconstruct zeta is to invert that operator. We have to invert a compact operator. That's not a good idea. You have to somehow regularize that problem to get rid of the zero singular values. If you make a different choice, it turns out it's not a compact operator that you need to invert. However, we have a nice sort of statement that for a whole class of models, whether the operator is compact or not, the origin is always in the spectrum, right? So there's always some kind of ill-conditioned nature to this inversion. And the reason this is ill-conditioned essentially comes from the same reason that the original problem was ill-posed. It's a reduction of an ill-posed problem, and it sort of, that property persists. So 2 points to take away from this slide is that your reconstruction operator actually depends on the surface velocity that you estimated. So if you make errors in that estimation, they will propagate. Yes. And you need to do regularization to sort of prevent this sort of inversion being unstable. Okay, so let's put all the pieces together. For a specific model, we can show that the linear observer with the incorrect bottom boundary satisfies the following bounds. So the error in the Q is upper bounded by the error in the parameter. The error in the surface velocity is upper bounded by the error in the bottom profile. And then these observer parameters appear here. And we've only been able to show this for the linear observer, but this same estimate seems to hold for the nonlinear case as well. Okay. You can also show that this reconstruction operator on the previous slide that I mentioned satisfies the following bound. So B times the error in the bottom boundary is upper bounded by the error in the surface velocity. This is what I was saying, that given the surface velocity, you were able to estimate the bottom profile. Given the bottom profile, you were able to estimate the surface velocity. You want to combine these two inequalities. You just want to chain them and end up with a statement of the following form, that the reconstruction operator hitting the final error is upper bounded by the initial error. So if you make 1 plus nu by lambda less than 1, you are able to, or sufficiently small, you are able to actually show the update is a better update. So you want to get a lower bound here on the zeta E final. You can't do that at this stage because 0 is in the spectrum, so you have to regularize. That induces a bias. But essentially, this is the inequality that tells you how to design the observer parameters. 1 plus nu by lambda should be as small a number as you can make it. But still, the observer should converge. Right? So you've got these sort of competing effects. You want to choose them such that the observer converges, but you want to choose them in such a way that this combination is a small number. All right, so just to summarize, given data, a model, an initial guess, an a priori bound on where the bottom profile is, there is a choice of the observer parameters such that the observer gives a sufficiently accurate estimate for the velocity at the surface. And we can then use the reconstruction as a minimization problem to get a better estimate. Okay. Here, the difference between the previous slide is I am using data from multiple times. I'm doing that really to prevent this problem that I might have a special kind of solution at one time. I want to use generic data, so I essentially minimize over a sequence of times this same cost function. Okay, so this is essentially the algorithm. It's essentially a two-step algorithm. You make a choice of lambda and nu, you run this, you get a better estimate. We are not able to turn it into an iterative scheme. Right? You would love to say, hey, you get a better estimate, go back up here again, improve, and keep on improving your estimates. The reason that doesn't work is precisely because of this statement here. Because this operator doesn't have a good lower bound, this operator is ill-conditioned. Because of that ill-conditioning, when you turn it into an iterative scheme, you actually introduce a new kind of instability. And at some point, whenever the error is in the direction of the smallest singular value, you amplify that error. And then that just propagates into your iterative scheme. So this is, in terms of a numerical method, we're kind of unhappy with it. As I'll show you, it works in some cases, but there is scope for improvement because we can't turn this into an iterative scheme. We can only do it once or a couple of times before the resolution degrades. So again, summary of the difficulties. We can address this by using generic data or summing over time. We have to use a model instead of the true problem. The observer allows us to solve for the Dirichlet condition in some sense, but ultimately the sensitivity to noise somehow persists in the form of an ill-conditioned matrix that needs to be inverted. Like that still persists. Okay, so here are some results. For a particular model, I basically give myself eta and run the nonlinear observer with this particular parameter choice of the observer parameters. The plot here, the dashed green line is the error in the surface velocity. So you can see that it, as a function of time, it sort of exponentially decays. This dashed black line is the linear expected decay rate. So the decay in the velocity is following the sort of programmed expected decay rate. And the blue curve is actually the error in the surface profile itself. So this seems to saturate at a higher value. It's not too much of a concern to us because we know the surface. So we don't need to reconstruct the surface. What we want to reconstruct is the other variable Q. The green line that's actually flat, that doesn't seem to show any decay, is actually the error in the potential. There's a difference between the error in the potential and the error in the velocity. The velocity is the gradient of the potential, right? And the error in the potential doesn't go to zero, but the error in the gradient of the potential goes to zero. What that says is the k equals 0 mode, the average potential, you've got wrong. But the average velocity you've got right. And that's related to an interesting fact that if you go back to these equations, these observer equations, and look at the linearized problem for the 0 mode, k equals 0, you realize it's not observable. It fails the observability condition. So k equals 0 is not an observable mode. Right? That's why the function doesn't show any decay in the error, but the derivative of the function shows a decay rate. Over here, I'm showing you what the reconstruction looks like. I started off with an initial guess that was flat, far away from the true surface, and then these red dots are my reconstruction. This is just telling you what the word regularized Boussinesque means in terms of models. Change a model, same story. Velocities decay, surface follows a similar pattern, expected decay rate is this. The potential is never accurate, but the velocities are accurate. A physicist would look at this and say, well, yes, potentials aren't real. Velocities are the physically meaningful quantity, so that's the only thing I should capture. Mathematically, it's got to do with a lack of observability for the k equals 0 mode. Right? And again, a reconstruction. All of these reconstructions, like a relative error in, let's say, the L2 norm or some such thing, it's about 10 to the minus 5 or 10 to the minus 10. This is all without any noise in the observation. When you add noise in the observation, I'm not even showing you the plots. They're so embarrassing. Right? Just, it's not a good idea. And it's entirely because of this part of the problem where we have to invert this ill-conditioned operator. Okay, so here's a quick summary. We've got a systematic way to produce models that we can use to do this parameter estimation of finding the bottom boundary profile. Theoretically, there's still an open challenge that why does the nonlinear observer converge? I don't know. I'd love to know the answer to this question, but what's interesting is, if you think about it, I'm not talking about one PDE. I'm talking about a class of PDEs, all of whom show convergence. And that's part of why I'm confused, like why should a wide class of problems just work? There must be some structural reason, I don't know what that is. And of course, the other problem is this noise issue. The observer model is very robust with noise, which is to say, if you introduce noise, then the output of the observer is proportional to that noise level, as it should be. If your observations are noisy, your reconstruction should be equally noisy. But the second step where I had this optimization problem, this minimization problem, that doesn't seem to respond nicely to noise. So it would be nice if we could sort of replace this second step by another process. We have some ideas. That sort of make more sense in finite dimensional cases, that is to say, ordinary differential equations. In particular, when the parameter is finite dimensional. In this case, the parameter is actually infinite dimensional. So it's still something that we need to look at. Okay, that brings me to the end of my talk. Thank you.
Am I audible? Yeah, so the information, the data that you are taking, the Dirichlet to Neumann map. So Dirichlet to Neumann data on the surface, you are taking on some part of the boundary or entire of the surface?
In some sense, the entire surface.
Entire surface. Okay.
That's right. That's right. It's a good question to ask. What happens when you take part of the surface? When you try to get data from an experiment, you tend to only see part of the wave, not the full wave. And so it's a very interesting and relevant question to ask, what happens when you only observe part of the surface? There are some difficulties with that, with even talking about then the Dirichlet-Neumann map. You have to talk about it carefully, because in some sense, you have no idea what the data should be on a part of the domain. And that's where this kind of, so the way that Fonteles and all treat it is they do elliptic continuation from the region that you know the information and spread it out. But unfortunately, that's not a numerically viable technique. And so it's hard to define what you mean by the boundary value problem, because part of the domain is completely undefined in terms of any boundary condition, which is to say you could put any boundary condition and get an equivalent problem. So it's a hard one to do, but I completely agree that it's a relevant question. I tried many things of extending the data. They all fail catastrophically. So yeah, I don't know the answer to that.
Thank you.